Hello, my name is Shahriar Shahriari, and this is a lecture as a part of a series of occasional lectures on topics in general topics in undergraduate mathematics. The topic of this lecture is the division algorithm. And versions of this appear in many books, including in two of my books, Approximately Calculus and Algebra in Action, a course in groups, rings, and fields. So let me start by telling you what the division algorithm is and what we're trying to do in this lecture. The division algorithm is actually a pretty intuitive thing, and one that might feel like it doesn't really need a proof, and it's quite possible to understand it at an intuitive level, and then it's fine. You can argue your way through it, but we want to give a full formal proof of it. Okay, so assume that you have m toys and n friends, and we're assuming that you have at least one friend. So n is at least greater or equal to 1. So m and n are integers. In fact, in the version we will prove m can also be negative. That won't work with our little toy problem here. But let's say that we have m toys and n friends. And what you want to do is you want to give each of your friends some of these toys, but you want every friend to get the same number of toys. Now, if m is not a multiple of n, you won't be able to divvy up all the toys in a way that everyone gets the same number of toys. So the best you can do if you're set on the fact that you want everyone to get the same number of toys is to live with the fact that you're going to have some toys left over. And so what the division algorithm says is that there's actually exactly one way to do that, as long as you want to make sure that the number of toys that are left to you is less than n. So if you have n friends, and you give each one of them a toy at a time, and you just keep doing that, at some point you won't have enough to go another round and give each person a toy, and that's what the remainder is going to be, and the remainder is going to be less than n. And if I do it, or you do it, or if you do it on Tuesday or Wednesday afternoon, the answer is going to be the same. There's just one way to do that, as long as you don't want too many toys left over. That's all the division algorithm says, and it's pretty obvious. Again, this is a tip of an iceberg in the sense that we are able to do the same kind of argument in general rings, which is not something I want to do right now. I want to only talk about integers, but also this is the cornerstone of a lot of number theory arguments and arguments that's used in places like in group theory, and therefore we want to sort of understand this perfectly well. So what this says one more time is that if you take m and divide it by n, m was the toys, n was the number of friends. If you take m divided by n, you will have a quotient q and a remainder r, and r is going to be greater or equal to 0 and less than n. And there's going to be exactly one q and one r that will satisfy this. There will be one, and there will be exactly one. So an example, if you have 47 toys and 7 friends, well, you could write 47 is 5 times 7, give every friend 5 toys, plus 12. So you might say that 5 is the Q and 12 is the R. This will not work because this 12 is not less than 7. If you don't make that condition that R is greater or equal to 0 less than n, then there's different ways of doing this. Like, for example, you could even write 47 is minus 2 times 7 plus 61. You could actually ask your friends to give you 2 toys each, and then you would be having an extra 61 toys. Or you could have 47 is 7 times 7 minus 2. That would also work. Give everyone 7 toys and then be short 2 toys. The point is that this equation m equals qn plus r is not unique. You can find lots of q's and lots of r's that work, but you can only find one for which r is greater or equal to 0 and less than n. So this part, the part that r is limited and it's non-negative and less than n, is actually the crucial part of the division algorithm. So in this problem with 47 toys and 7 friends, the one equation that the division algorithm is promising us is that 47 is 6 times 7 plus 5. This division algorithm is used in many places, including in group theory and in ring theory. In ring theory, we actually think of this in much more general context of commutative rings and try to see which rings have this kind of a division algorithm or not. And that's a longer story that we will get to when we do if you watch the videos on ring theory. In the proof of the division algorithm, and actually in the proof of the fact that the greatest common divisor is a linear combination of the two numbers, we will use the well-ordering principle. And this well-ordering principle is the following thing. It says that if you have a set of non-empty set of non-negative integers, so you have a bunch of, not zero, a bunch of integers, and they're all non-negative. They're 0 or bigger. In such a case, S always will have a smallest element. So because they're bounded below by 0, the lowest one is 0, possibly, maybe 0 is not there, but whatever integers you have, as long as they're non-negative, there will be a smallest one. If this was just integers, you couldn't say that, because you could have integers going down to negative infinity and not there be a smallest element. But as long as your set consists of only non-negative integers, always there will be a smallest element. So if you want to write it formally, you say that there's an M in this set S that is less than or equal to every element of S. Now you can take this as an axiom of integers. It's something that we know about integers, or you can actually prove it using induction if you like. In fact, this is equivalent to the principle of mathematical induction. So, for example, if you know the well-ordering principle, how would you prove the principle of mathematical induction? So what does that mean? That means, like, how would you know induction works if you know the well-ordering principle is true? So the induction says you have some statement Pn that you want to prove. You've already proved the first case P1. You've proved that Pk minus 1 proves Pk. And you want to now know, why is it true? Why is it that P of n, the statement for all n, is true? I mean, that's what induction says, that if you prove the first one and then prove that k minus 1, first one proves kth one, then it's true always. But here we want to prove that it's true for always, as long as we know the well-ordering principle. And so the way we do that is we say that, okay, look at all the statements Pn. Maybe you're not convinced that they're all true. So some of them maybe are true, some of them are false. Let S be the set of integers for which the set of n such that P of n is not true. And this is we are assuming that it's non-empty, that some of them are not true, and those are all non-negative integers. Then if we accept the well-ordering principle as an axiom, then that set will have its smallest element. That smallest element can't be the first element, because by induction, by the base case of the induction, you'd already proved that P of 1 is true, so 1 can't be in this set, and our statements start P of 1, P of 2, P of 3. So the things in this set S could be any integer greater or equal to 1, the ones for which the statements are not true. But 1 can't be there because you already proved that by base case. So the smallest there would be some k, at some k that P of k is not true. But if that's the smallest in that set S, then that means anything smaller is not in that set. So that means P of k minus 1 is true. But because you had proved by induction that P of k minus 1 is true implies P of k is true, P of k could not have been in the set either. And that's a contradiction, proves that that set S must have been empty, and therefore all statements of the form P of n are true. So using well-ordered principle, you can prove induction. Using induction, you can prove the well-ordering principle also. So I'm just not going to do that right now, but you might want to think about that. It's not that difficult to do. So this is just another way of saying induction, but it's something that in elementary number theory we use often, and in group theory as well. So let me state the division algorithm properly, and then I will prove it, give a formal proof of it. So Z is, first of all, this Blackboard Z stands for the set of ordinary integers, and the division algorithm says that if you give me an integer greater or equal to 1, an integer greater or equal to 1, n, and then you give me some other integer, m can be positive, negative, 0, anything, then I can divide m by n and get a quotient and a remainder. And the quotient and remainder are unique. So there's two unique integers that division algorithm promises to me, Q and R, such that M is Qn plus R, and R is not that big. R is between 0 and n. So I took M and divided it by n. So M was my toys, and n was the number of friends I had, and I gave each one of them Q, and I'm left with R. Now, the division algorithm says there's only one way you do that, as long as you're making sure that the remainder could be 0, there could be no remainder, or no more than n. If you're willing to have more remainders, then Q and R would not be unique, but if you larger remainders. But as long as the remainder is between 0 and n, including 0 but not including n, then this quotient and remainder will always be unique. And for any two integers, m and n, you can take m and divide it by n and get such a thing. I'll introduce another notation that we don't actually need for the proof, but for later on, it's sort of convenient to have. And also, this division algorithm allows us to talk about such things. If A and B have the same remainder when you divide them by n, then the notation that we use is this congruence notation. We say that A is congruent to B mod n, and we write A triple line B mod n. That's the notation we use in number theory. In group theory, sometimes we just say equals. But these two things are equal if you are in the world, for example, Z mod n Z. And again, we read this A is congruent to B modulo n. And so, for example, if in the situation of the division algorithm, if R is the remainder of M when you divide by n, one way to write that is that M is R mod n. M is R mod n. Now, when you write A equals B mod n, that doesn't necessarily mean that B is the remainder of A mod n. It could be. It just means that A and B have the same remainder if you divide them by n. Now, if you divide M by n and the remainder is R, and if you divide R by n, which is a number between 0 and n, well, the quotient will be 0 and the remainder will be R. So M and R will have the same remainder when you divide them by n. Okay, so now let's get on with the proof of the division algorithm. So what is it that we have? We have an integer n that's greater or equal to 1 and another integer m, and we want to show that there are unique integers q and r such that m is qn plus r, and then r is greater or equal to 0 but less than n. I'm first going to show that there are such things, and in the next slide, I'll show that they are unique. That if I do this and find the quotient and remainder, and you do it, we'll get the same thing. Again, as long as the remainder is small enough. Okay, now the point is that we want q and r such that m is qn plus r. So, but if you know one of them, then we know the other one. So for example, if you have it q, then you can let r be m minus qn, and that will work. The only problem will be if r is not small enough. And for that reason, what we want to do is we want to make sure that m minus qn is as small as possible. So we want r to be non-negative, and we want it to be small. But if we want it to be of the form m minus a multiple of n, so that's that multiple is the q, and then I have m equals r plus qn. So for that reason, I will look at all things of the form m minus kn when k is an integer. These are my candidates for r. Like if I think about it, because I want m to be qn plus r, I want r to be of the form m minus something times n. So I'm looking at the set of all such things. Hopefully, r is among these. And in fact, because I want r to be non-negative and small, that's what I'm going to be looking at. First of all, I'm going to ask, does m necessarily have any non-negative integers? And the answer is yes. Why? Because k can be negative. So n is greater or equal to 1, and k, if you put k negative, that k minus kn becomes a positive thing. And it doesn't matter what m is, how negative it is. You can make that k a large negative number and overwhelm m and make that positive. So therefore, m certainly has non-negative and positive integers in it. So if it does, and it might have some negative integers in it also. So what you can do is just look at the non-negative integers in n. Forget the negative ones. Look at the non-negative integers in n, and let r be the smallest one. In that way, we have ensured that r is non-negative, which is something we want, and small. In fact, the smallest of the form that we want to work. And so hopefully this R is the R that we're looking for. So far we know that R is greater or equal to 0, and R is of the form M minus Qn for some integer Q. Why? Well, because it's an element of the set M, and M consists of all elements in M were of this form. Okay, so we have that. So are we done? No, the only thing remaining is that we have to show that R is less than N, that if I take the smallest thing in M, it's actually less than N, because we want that, and there is no reason why it is so far. So the question is that what happens if R is greater or equal to N? Could we be in a situation where we go in M, try to find the smallest non-negative integer in M, and we do, but that guy is greater or equal to N, then we're in trouble. But the point is that if R was greater equal to N, then R minus N would be non-negative. Well, because R greater or equal to N, bring N to the other side, you get R minus N greater or equal to 0. But R minus N is non-negative, and it's smaller than N, and it's in M. Why is it in M? Because if you subtract an N from M minus Qn, you get M minus Qn minus N, and that's M minus parentheses Q plus 1 N. And so that's also of the form of elements in M. So R minus N will be something that's in M, it's non-negative, and it's smaller than R. So what's wrong with that? Well, the thing that's wrong with that is that we picked R to be the smallest non-negative integer in M. And if R is greater than or equal to N, apparently we didn't. We failed. We picked the wrong one. So that's a contradiction. So that shows that R is also less than N. And so I've got my R and Q with M equals Qn plus R, and R greater or equal to 0 less than N. How did I find that? Well, R, I just told you how I found. Where did Q come from? Well, Q is that R was of the form M minus Qn, M minus something times N. That something is Q. And the reason that works is that you can bring the Qn to the other side and you get M equals Qn plus R. And we have already proved that R is less than greater or equal to 0 and less than N. So now what I have to do is to prove to you that if you did it, you would have got the same R and Q as I did it. I mean, if you use the same method, of course, you would get the same thing. But maybe you can find Q and R in some other way, and then they're going to be different than mine. So again, we have N is greater or equal to 1, an integer, and M is an integer. M was the set of elements M minus Kn, where K was any integer, and R was the smallest non-negative integer in this M. And we also know that M is Qn plus R, and R is greater or equal to 0 less than N. That's what we just proved. And the question is that why are Q and R unique? Why can't someone else come up with a Q and R such that M equals Qn plus R and R is still greater or equal to 0 less than N? Whenever we want to prove uniqueness, one approach is to say, okay, well, let's say it wasn't unique. Let's say there was something else too. So assume that M was also Q1N plus R1, and R1 also was greater or equal to 0 less than N. So I now assume that Q1 and R1 are not the same as Q and R and get a contradiction, or better yet, not make that assumption and then prove that Q and Q1 must be the same, R and R1 must be the same as well. So if you come up with any Q1 and R1 that satisfy these conditions, what conditions? M equals Q1N plus R1, and R1 is greater or equal to 0 less than N, then what I want to prove is that R1 is R and Q1 is Q. That would show that no matter how you do it, you're going to get the same R and Q that I got from that process that I did before. And actually that process also tells you how to find that remainder. It just says start with M and start taking out N's as much as you can before you become negative. And right before you become negative, you've got the remainder, which is there. If you think about the toys, that's obviously what you would do. Okay, so now what about R1? Well, R1 is M minus Q1N. So that means that R1 is M and is in M because it's of that form. But R was the smallest non-negative integer in M, so R is less than or equal to R1. Maybe they're equal. Maybe there's but if it's equal, that's actually what I want to show. But R is going to be less than or equal to R1, since R is the smallest non-negative integer in M. So that means that R1 minus R if R1 is greater or equal to R, then R1 minus R is greater or equal to 0. It's also less than N. Why is that? Well, because R1 is less than N. And so if you subtract something from it, you're going to get something less than N. So this R1 minus R is between 0 and N. But also, if you look at it, you see that R1 minus R, instead of R1, I can put M minus Q1N. That's what it is. And instead of R, I can put M minus Qn. If you solve for R in M equals Qn plus R, I can put that. Then I can combine the M's cancel, and then I can factor out an N, and I get N times Q minus Q1. Now, this R1 minus R equals N times Q minus Q1 means that Q minus Q1 is greater or equal to 0. It can't be negative. Why? Well, because R1 minus R was greater or equal to 0. N is greater or equal to 1. And so this guy got to be positive, not negative, because if it's negative, then R1 minus R would be negative, and that's not true. So Q minus Q1 is greater or equal to 0. But could it be actually greater than 0? If it was greater than 0, then that would mean that R1 minus R is N times, this is an integer, so it would be, the smallest it could be would be 1, and so that would be N. But if it was 2, then it would be 2N, 3N, 4N. It would be greater than N. But we also know that R1 minus R is less than N. And so regardless, Q minus Q1 cannot be greater than 0. If it was, we would get a contradiction. And so that means that Q minus Q1 is 0. But if Q minus Q1 is 0, then N times 0 is 0. And so R1 minus R is 0. But Q minus Q1 being 0 means that Q equals Q1, and R1 minus R being 0 means that R equals R1, and we're done. So we proved the division algorithm. Again, if you think about toys and friends, both the proof and the statement are pretty common sense, except here we just wanted to make sure that there's no skeletons in the closet, and look under the hood and see that we really use the well ordering principle. So we're really doing this by some form of induction. Okay, so let's show you an application of the division algorithm. The division algorithm is something that in elementary number theory you use all the time, as well as in group theory and in ring theory. In all of those fields, division algorithm is something that is used day in and day out. And I just want to give you one simple example right now. And the second example will be actually when we want to prove something about the greatest common divisors. Okay, so let's say that you looked at n, the number 13, that was maybe your favorite number, you squared it, and you didn't have anything better to do, and so you divided that by 8. And well, you couldn't quite divide it, so you got a remainder, and you got a remainder of 1. Okay, that's the remainder that you get. Okay, so then you again, you're bored, and so you do the same thing with 14. You square it, and you find a remainder of n squared when divided by 8, and this time you get 4. Okay, that's not surprising. When you divide things by 8, you expect the remainders to be 0, 1, 2, 3, 4, 5, 6, or 7. Those could be the remainders, and so you got 1 and 4. That's good. So maybe we'll get the other ones as we go along. Then you put 15 in, and you get 1 again. All right, no big deal. So again, every time we're squaring the integer and finding the remainder when divided by 8. 16, well, 16 itself is divisible by 8. So when you square it, of course, it's going to be divisible by 8. And so the remainder is going to be 0. Okay. Then you go to 17. You just keep going. And you see that the remainder is 1 again. So this 1 keeps coming up. And then you go to 18 and you have 4 again. And then you just keep going. And you see that a pattern that the remainders seem to be 1, 4, 1, 0, 1, 4, 1, 0, 1, 4, 1, 0, and they keep going. In particular, the remainder is never 2, never 3, never 5, never 6, never 7. Now, if that's true, that was a fact that was all there since time immemorial. Did you know about it? This is just a fact that you might not have never known, that if you take any integer and square it and you divide it by 8, the remainder is never 2. The remainder is never 3, never 5, never 6, never 7. But it's 1, 4, 1, 0, and it's in this, that comes in this pattern. So the question is that, does the pattern continue? By the way, when we're talking about a remainder, since we know the remainder is unique, that's why we can sort of make this table. But to prove the pattern, we will also use the division algorithm. Just before starting the proof, I can tell you that you can actually make money out of this pattern. You could go to a friend and you say that, okay, we'll pick a random number. Maybe we'll open a book and look at the page number, and we'll square it, and we'll divide it by 8. And if the remainder is 1, 4, 1, or 0, 1, 4, 1, 0, that's 4 things, I'll get $1. But if the remainder is 2, 3, 5, 6, or 7, 5 things, you'll get $1. So I'm giving you better odds, and we'll do that. But you know that you're always going to win. If you don't want to, after a few rounds, spook your friend, give him one of something like 4 or 0. Also, like you win if you get 0, blah blah. I only win if I get 1 and 4. No, that's all I need. Okay, so let's see. How would I prove this? That this pattern is appearing. First of all, note that I see that the pattern has a freak, like every fourth one seems to be the same. So it's 1, 4, 1, 0, and then it appears. So it seems like the integers are come into 4 types, and they're sort of repeating after 4 types. That gives me a clue that what I want to do is I want to look at the remainder of this integer n when divided by 4. So I take n and I divide it by 4, and the division algorithm now comes in and tells me that the remainder is going to be either 0, 1, 2, or 3, and it gives me 4 cases. So either the remainder is 0, 1, 2, or 3. This is the original n, not the n squared. So the original n, I'm not making as in assumptions. If you divide by 4, the remainders are going to be 0, 1, 2, or 3. So now we have several cases. The first case is when the remainder is 0. Now I'm using that notation that I introduced, n is 0 mod 4. All that means, that's a shorthand for saying if you take n divided by 4 and choose a remainder that's between 0 and then 3, 0, 1, 2, or 3, I'm assuming that remainder is 0. So in this case, what does that mean? Then that means that n is of the form 4k. It's a multiple of 4, because when you divide it by 4, you don't have any remainder. So it's a multiple of 4. But then what's n squared then? So then n squared is going to be 4k quantity squared, which is 16k squared. And you can factor an 8 out, and then that says that n squared is also 0 mod 8, because it has a factor of 8. So if n is 0 mod 4, n squared will be 0 mod 8. So in this case, I got the remainder is 0. Case 2 is that what if when I divide by 4, the original n, the remainder is 1? Well, what kind of a number is that? Then that means that if you take 4s out of n, you only think at the end of the day 1 is left. That means that n is of the form 4k plus 1, a multiple of 4, but then the remainder is 1. Actually, that's what the division algorithm tells us. You divide by 4, the remainder is 1. So n is of the form 4k plus 1. That's exactly what the division algorithm told us. I mean, this idea of taking 4s out and 1 is the win. That's the intuitive idea. But the division algorithm told us that you get qn plus r. And so the q here, I'm writing as k. So now what will n squared be? Well, you've got to square this guy. And if you square this, a plus b squared is a squared plus 2ab plus b squared. You get 16k squared plus 8k plus 1. Now, how is that in terms of what is the remainder of that when divided by 8? Well, the division algorithm tells me you know the remainder if you can write it as 8 times something plus 1. So again, I'm dividing by 8. And here, both 16k squared and 8k are divisible by 8, so I can factor an 8 from them. And the 1 is the remainder. So that means that n squared, when you divide by 8, you get remainder 1. Case 3 is if n is 2 mod 4. Has remainder 2 when you divide by 4. Then that means, again, by the division algorithm, that n is of the form 4k plus 2. If you square that, you get 16k squared plus 16k plus 4. Again, the first 2 terms are divisible by 8. So this guy is the remainder. And so n squared has remainder 4 when divided by 8. So one case left, and that's when n is 3 mod 4. And then that means that n is 4k plus 3. If you square that, you get 16k squared plus 20k plus 9. So is the remainder 9? No, because our remainder, remember, has to be between 0 and 8. And so what I do here is I write this as 16k squared plus 24k plus 8 plus 1 plus 8 plus 1. And the 16k squared plus 24k plus 8 is divisible by 8. And then the remainder is 1. So we see that in two cases, we get remainder 1, and then we get the 0 and the 4. And we see the pattern. We get 0, 1, 4, 1, 0, 1, 4, 1, which is the pattern that we got. In fact, we now know more things. Like, for example, now you know that if you take an odd number, now an odd number can't be of the form 4k. That's an even number. 4k plus 2 is also even. So any odd number is either of the form 4k plus 1 or 4k plus 3. And now we know that if you take an odd number, square it, and divide it by 8, the remainder is always 1. That's an amazing little fact that maybe you didn't know, but now you do. So if take any integer, square it. Well, not any integer, any odd integer, square it, divide it by 8, and find the remainder. You always will get 1. Why is that? Division algorithm. Okay. This is the end of this lecture, and here's a list of other lectures that might be of interest to you. This lecture was on the division algorithm for ordinary integers. In a subsequent lecture, I use the division algorithm to show that greatest common divisors for ordinary integers are going to be linear combinations of those integers. In another video in the group theory section of my YouTube, I talk about the group of units of Z mod NZ. And again, their division algorithm is used for a variety of uses, including finding what are the units of Z mod NZ, as well as for showing that Z mod NZ under multiplication is associative. In the ring theory section, we will study Euclidean domains, which are generalization of the division algorithm. The rings in which we have division algorithm. Rings are generalizations of integers, and some of them have the division algorithm, and those tend to be pretty important, and they're called Euclidean domains. See you in the next lecture.